Dear students, here comes a video that discusses properties of eigenvalues. Property 1. Eigenvalues of a square matrix A and the eigenvalues of the transpose of the square matrix A dash are identical. This property looks very much similar to the property of the determinant, which says that the determinant of a square matrix and the determinant of the transpose of the square matrix are the same because the determinant of a matrix is unchanged if the rows and columns of the matrix are interchanged. Let's look at the proof of this property. Consider an nth order square matrix A and the transpose of the square matrix represented by A dash. That is, the first column of A dash is the first row of A, the second column of A dash is the second row of A, and so on. Since eigenvalues are the roots of the characteristic equation, we are interested in evaluating the eigenvalues, that is the characteristic equations of A and A dash, which are given by the expressions determinant of A minus lambda I equal to 0 and determinant of A dash minus lambda I equal to 0 respectively. When you look at the matrices A minus lambda I and A dash minus lambda I, you notice one thing, that is, the first column of A dash minus lambda I is the first row of A minus lambda I. The second column of A dash minus lambda I is the second row of A minus lambda I, and so on. Hence, A dash minus lambda I is the transpose of A minus lambda I. Since these two matrices are transposes of each other, their determinant expression will also be the same. That is, the resultant characteristic equation for both these matrices A and A dash will be the same, because the determinant of a matrix is unchanged if the rows and columns are interchanged. Since the equations themselves are identical, the roots of the equation, that is the eigenvalues, will also be the same. Thus, we can conclude property 1. Moving on to property 2. Sum of eigenvalues equals sum of elements on the principal diagonal. We prove this property for a 3 by 3 square matrix. We may easily generalize this for an nth order square matrix using the concept of mathematical induction. If you consider a 3 by 3 square matrix A and evaluate the expression determinant of A minus lambda I, expanding this determinant, you get a cubic equation, and you notice that the coefficient of lambda square itself represents sum of diagonal elements. A11, A22, A33 are the diagonal elements, and coefficient of lambda square represents the sum of diagonal elements. Hence, we are not interested in the other terms of this particular cubic equation. If you assume that lambda 1, lambda 2, lambda 3 are the roots or the eigenvalues of the characteristic equation given by determinant of A minus lambda I equal to 0, you can easily write the characteristic equation in terms of linear factors involving lambda 1, lambda 2 and lambda 3. Because for any cubic equation, if you know that alpha, beta, gamma are the roots, you can easily express this cubic equation in terms of linear factors of the roots alpha, beta and gamma. Having expanded these linear factors, again you get the coefficient of lambda square, and you are not interested in the other terms. Looking at the coefficients of lambda square in both these equations, which are actually the same, you can easily equate the coefficients of lambda square and you get the conclusion of the proof, that is, sum of diagonal elements of a matrix equals sum of eigenvalues of that particular matrix. Moving on to next property, which says that product of eigenvalues of a matrix equals determinant of the matrix. If you consider an nth order square matrix having n eigenvalues, you can easily write the characteristic equation determinant of A minus lambda I as the linear factors involving lambda 1, lambda 2, etc. lambda n, which are the eigenvalues. If you substitute lambda equal to 0 in both LHS and RHS, the LHS reduces to determinant of A and the RHS involves term which consists of product of eigenvalues along with a minus 1 multiplied n times, since n eigenvalues are considered. When you consider the product minus 1 the whole raised to n into minus 1 the whole raised to n, you can reduce it as minus 1 the whole raised to 2n, which is an even power of minus 1 and will always give the output 1. Hence, the determinant of A is always equal to product of eigenvalues. The next property says that if lambda is the eigenvalue of a non-singular square matrix A, then 1 by lambda will be the eigenvalue of the corresponding inverse matrix. Determinant value of A equal to non-zero. That is the meaning of non-singular matrix. If lambda is the eigenvalue, automatically you get the equation A minus lambda I into x equal to 0, which is the characteristic equation. From this equation, you may write Ax equal to lambda Ix, and you may not write I because multiplication of an identity matrix to another matrix does not cause any change. So you get the expression Ax equal to lambda x. When you pre-multiply both sides by A inverse, you get the corresponding expression A inverse into Ax equal to A inverse into lambda x. Combining A inverse and A, you get identity matrix, and lambda is just a scalar multiplied to the column matrix x, so it can be taken outside the matrix multiplication A inverse into x. You get the expression x is equal to lambda into A inverse x. From here, if you take lambda to the LHS, you get 1 by lambda into x equal to A inverse x, and you get A inverse x minus 1 by lambda into I into x equal to 0. This expression is actually of the form A minus lambda I into x equal to 0. Hence, this can be considered as the characteristic equation of A inverse with 1 by lambda as the eigenvalue. So, by looking at this expression, you can easily conclude that 1 by lambda is the eigenvalue of A inverse whenever lambda is the eigenvalue of A. You arrived at this expression by looking at this expression, because when you take 1 by lambda into x to the LHS, you can take the column matrix x common outside, and multiplication of the identity matrix to the scalar 1 by lambda does not cause any change for the matrix multiplication. Next property says that if lambda is the eigenvalue of an orthogonal matrix, then 1 by lambda will also be its eigenvalue. What do you mean by an orthogonal matrix? It's a special type of matrix which satisfies the standard property A dash into A equal to identity matrix, which is equal to A into A dash, where A dash is the transpose of A. It also satisfies these properties A inverse equal to A dash and determinant of A is equal to plus minus 1. This is the standard property, and from this property itself you can arrive at these two properties. We'll learn more about orthogonal matrix in the upcoming videos. If lambda is the eigenvalue of a matrix A, automatically A inverse will have 1 by lambda as the eigenvalue from the previous discussion. In particular, for an orthogonal matrix, A inverse coincides with A transpose. Hence, 1 by lambda becomes the eigenvalue of A transpose as well. From property 1, we studied that A and A transpose always have same eigenvalues. Hence, 1 by lambda will also be the eigenvalue of A. So, if it is given that A is an orthogonal matrix with lambda as the eigenvalue, then 1 by lambda will surely be its another eigenvalue. How to prove that the orthogonal matrix satisfies the property determinant of A equal to plus minus 1? It follows from the standard property of orthogonal matrix, which says A into A transpose equal to identity matrix. When you take determinant on both sides, determinant of identity matrix is always 1, and determinant of product of matrices can be written as determinant of AB equal to determinant of A into determinant of B. Hence, this is written as product determinant of A into determinant of A transpose, and we always know that A and its transpose A dash always have same determinant expressions or values. Hence, you can replace A dash by A itself and you get the square of determinant A, which equals 1. The only possibilities for determinant of A are plus 1 or minus 1. Hence, you can conclude the property of orthogonal matrices. Thank you all and have a nice day.